We've made mention previously of the FIB and RIB structures, and we want to outline those a bit more clearly in this video. These structures within an IP network perform two distinct functions. Let's take a closer look, starting with the FIB, the forwarding information base. The FIB is also sometimes referred to as the CEF table or the IP forwarding table, and this is used to make IP destination prefix-based switching decisions. The FIB contains the interface number and next hop information for each reachable destination network prefix. The FIB, as we've mentioned in regard to Cisco Express forwarding, is also used in conjunction with CEF. The FIB itself is a direct copy of the routing table. Each time a routing change occurs and the routing table is updated, the FIB is also updated to reflect those changes. With CEF, the FIB is used to make IP destination-based switching decisions, which takes the CPU out of the equation and creates a faster, more lightweight switching process. One of the things to note about the FIB is that, generally speaking, the number of entries found within the FIB may influence the ability of the router to forward traffic quickly. The more entries there are within the FIB, the longer it could take for route lookup to happen. But these days, that isn't much of an issue with our modern equipment. We have very fast ASIC-based forwarding that is nearly equal to line speeds. On Cisco routers that have the ability to use distributed CEF or DCEF, a copy of the FIB would be applied to each of the line card modules. This again is another way that the CPU is offloaded in order to increase the amount of traffic that the device can handle without affecting performance. The RIB, or routing information base, is the location where all information related to IP routing is stored. This is not specific to any particular routing protocol, but rather it's used by all protocols, such as OSPF and BGP. Anytime a routing protocol learns about a new route, that route is inserted into the RIB. When a previously learned route becomes unreachable, this route is first marked as unusable and will eventually be removed completely from the RIB if the route remains down. And the amount of time that it takes for that to happen, that's dependent upon the routing protocol that's in use and the particular timers that are related to the protocol from which the route was learned. Within the RIB, we'll find all routes that have been learned dynamically through protocols such as OSPF, and we'll also see directly attached networks and any manually configured static routes as well. An important distinction is that the RIB is not used for traffic forwarding, and it is not advertised to the rest of the networks that are attached to the router. In order to more clearly outline the difference between these structures, let's take a look at this overview. We know that routers have various ways in which they can learn about the best paths toward specific destinations. That can include directly connected devices, statically configured routes, and of course, routes learned through dynamic routing protocols. And here at the top of this overview, we see routes learned dynamically being represented. Each routing protocol has its own internal structure used for routing. So where we see BGP, EIGRP, and OSPF in this example, we can see those respective structures: the BGP table, the EIGRP topology table, and the OSPF link state database. Each of these routing protocols leverages and updates their own structures based on updates that they exchange with neighboring devices, and they do that in order to build a picture of the network. Each one has their own way to determine the best route for traffic based on their route selection algorithms. This happens in different ways depending on the protocol itself, but in each case, the results are inserted into the routing information base, the RIB, and those are based on administrative distance for the route. So for example, if a route is learned via OSPF and BGP, OSPF will be the preferred route because it has a lower administrative distance than internal BGP. Now, you may be wondering, why don't we use this information for packet forwarding? Why don't we use the RIB for that? It seems to have everything we need. And the problem is, some of the entries contained within the RIB may have next hop addresses that are not directly connected. For example, this is really commonly seen with BGP or with statically configured routes. And this is where the forwarding information base comes into play. The FIB contains a copy of the routes found within the RIB. This information is used to resolve next hop addressing, since the FIB has knowledge of the layer 2 data required for forwarding. The FIB will determine which outgoing interfaces are needed for a particular network destination. The completed FIB or CEF table is then capable of making layer 3 switching decisions. As we've already mentioned, any updates happening to the RIB will be copied over to the FIB as well. So that's an overview of the forwarding information base and the routing information base, and how those two structures work together for efficient traffic movement within an IP-based network.